So here we are. We just read the question. We have our formula for decanol, and we're filling in the Lewis structure for decanol. Carbon always wants 4 bonds. Any bonds that are not shown to other carbons have to be hydrogens. All of the middle carbons here will be carbon bonded to 2 hydrogens and 2 carbons. And the end one will be bonded to 3 hydrogens. So let me fill all those in. There we go. Oh, and it's a Lewis structure, so put in all your pairs of electrons. Oxygen, that oxygen has 2 pairs of electrons. Now, if this were a skeletal structure, you would draw 10 carbons like this. 1, that's just my point right there. 2, 3, 4, 5, 6, 7, 8, 9, 10, with an OH at the end. And so that's why I love skeletal or line bond structures. They're much simpler. But what we need for this problem is actually the Lewis structure, because we're going to need to count up all these bonds. Let's see. Now I'm going to write the balanced combustion reaction for decanol. I'm going to use this empirical formula. No, molecular formula. It is both of them, by the way, I guess. C10H22O. Combustion always adds oxygen, always produces carbon dioxide and H2O. Now I will balance this. I put a 1 in front of my most complicated compounds. I now have 10 times 1 carbons, so I must have 10 carbon dioxides. I have 1 times 22 hydrogens. Hydrogens come 2 at a time, so there's my 11 times 2 is 22 hydrogens. And last but not least, I balance my oxygens. I have 20 right here. I have 11 for a total of 31. And then I have 1 oxygen right here, which means I only need 30. Since oxygens come 2 at a time, 15 goes right there. Okay? And that should be balanced. And hint, I have hopefully set up all of these so that they all balance with a 1 right here. So you will not need any 2s. You will not have any fractional coefficients. At least that was my intent. Okay. Now let's see. So writing the balanced combustion reaction, done. Drawing correct Lewis structures for all of the reactants and products. Well, we've drawn one of them. Now let me draw. So by now, when you get to this question, if you've done the recitation and you've done the previous problems, you should be pretty good at drawing Lewis structures. But I will tell you that oxygen has a double bond in it, O2. Carbon dioxide has 2 double bonds in it, and H2O has 2 oxygen-hydrogen single bonds. Let me stop for a second and see if there are any questions. Well, let me just cross this out. Any questions so far? If not, then now showing how many of each type of bond are on the reactants and product sides. Okay, so now I'm going to make a little list of the bond and then the energy. I'll do these for the reactants. And I'll do this for the products as well. Bond energy. Okay. And do include the coefficients. Coefficients. Okay, what do I mean by that? What I mean by that is, okay, for this first molecule, I'm now going to count up all the bonds in this molecule. So I'm going to start with carbon-carbon, single bonds. I have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 carbon-carbon single bonds. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 carbon-hydrogen single bonds. I have 1 carbon-oxygen bond, single bond, and 1 oxygen-hydrogen. And it doesn't matter which order you put them in, but that's how I put them. And those are all the bonds in this first molecule right there. Then I have 15 oxygen-oxygen double bonds. So I'm going to list those as 15 oxygen-oxygen double bonds. And that's all of the bonds in the reactants. On the product side, I have 2 carbon-oxygen double bonds in each molecule, and I have 10 molecules. So actually I have 20 carbon-oxygen double bonds. And I'm going to put an asterisk right there, and I'll talk about that in a minute. Maybe what helps is putting your coefficients right here too. I don't know if that helps. Finally, I have in each H2O molecule, I have 2 OH bonds, and I have 11 times 2, so I have 22 OH bonds. Now, all I have to do is add them up, or I have to look them up on my conversion table. So I see, let's see, I don't think I can get this all on the same page with zooming in this much. But a carbon-carbon single bond, carbon-carbon is 356. 9 times 356. I'll zoom out again a little there, I guess. There we go. Carbon-hydrogen from that list is 416. Carbon-oxygen, 336. Oxygen-hydrogen, 467. And now the double bond. So the double bond for oxygen would be double bond 498. And we'll end up adding all those up in a minute. Now, on the product side, we have 20 carbon-oxygen asterisks. And the asterisk means if you go down to the double, triple, single, double, triple bond table, it says for carbon dioxide, the C double bond O bond is 803 kilojoules per mole. And I'm going to put in a minus here. Okay. That's because for products, bonds are made. And when bonds are made, you release energy, and that minus sign means energy is released. Oxygen, hydrogen is also over here, so it's going to be 22 times minus 467. And that's all we have to add up on the product side. Now when we add everything up, and remember, I gave you the answer here, and fingers crossed that answer is correct. I add up all of these. 9 times 356 plus 21 times 416 plus 336 plus 467 plus 15 times 498, 20,213. Now, for the product side, I get 20 times 803 minus plus 22 times 467 minus negative 26,334. That's kilojoules per mole. And finally, my delta H reaction equals reactants plus products. $20,213 minus 26,334. I'm adding it, but it's a negative number. And again, I have my fingers crossed for this. 20,213 minus 26,334. Negative 6121 kilojoules per mole. Final answer. So all of our work paid off. And again, our process, and this is very engineering, which is why I love it. So you take a reaction, you analyze it in terms of your bonds that are in there. The reactant bonds are bonds broken. Your product bonds are bonds made. And we're using just an average bond except for carbon dioxide. Carbon dioxide, that one's specific. But we're not differentiating which molecule these bonds are in. There's an OH bond in water, and it's 467, whether it's made or broken. Here it's made. An OH bond in Decanol is estimated at the same thing. Are they necessarily exactly the same? No, but this is an estimate and a calculation. And these estimates are particularly important when you look at burning reactions and combustion of different materials. So if you wanted to know how much energy you were going to get by burning Decanol and you didn't want to actually burn Decanol, you could estimate it. And the estimates are usually within 5%, which is pretty good for a general technique. Very long problem. I managed to fit it on one page. Does anybody have